Okay, I want to go over this problem with you. This was a problem you had on your homework. Had a little trouble getting through it. It has a wheel with a wire wrapped around it, and the wire comes off here, and a mass is suspended by that wire. Okay, you're given, and at time zero, the mass is released and it travels down a certain amount of distance in time, and you're given that distance h, and you're given that distance, and you're given the time that it takes to go that distance. You're also given the mass of this block, and you're given the radius of the big wheel up here. You're asked to find the mass of the wheel. Okay, so you approach this using this tau is equal to I omega is equal to F times R, F the torque there. That works, but it's kind of a hard way around it, and I think there's a more simpler way here. Plus, you guys are studying about energy, conservation of energy. On the test, he's going to want it worked this way with the conservation of energy. So we're going to forget this tau for now, all right? Conservation of energy. What we're doing, you're transferring this potential energy of this mass. It comes down here. It's taking a certain amount of the potential energy, and it's converting that into the kinetic energy of the mass at the end of the run here, plus the rotational energy of the wheel up here. So that's not too terribly different than what you worked with before. So the equation is mgh, the potential energy, is equal to 1/2 mv squared, the kinetic energy of the block, plus 1/2 I omega squared. Now, one thing I need to mention here, on other problems you've worked where a single object is spinning and translating, okay? This one you've got two different objects. One is translating and the other is spinning. They have different masses. So on previous questions, the masses have all canceled out. Not so this time, because they're different masses. So this I, it is a disk, so the moment of inertia is 1/2 mr squared. Now the m is the big M, the mass of the disk. Okay? Omega squared is v squared over r. Omega is v over r, same as it always has been, because a point on this disk as it turns, however far it turns, is going to be however far this drops. The velocity of a point on this on the rim of the disk is the velocity that the mass is descending by. Okay, so that's the key. What do we know? We know you're given the small m, you're given g, you're given h, m, and you're given again this v squared over r. We'll look at that, but so we need to find v here. We're looking for this m right here. We're looking for that m, the big M, mass of the disk. So we got to know what v is. Well, okay. The problem is stated that it starts from rest, it goes a certain distance in a certain amount of time. That just screams of our old kinematic equations. As a matter of fact, the one that I'm using here, S equals S0. I think you may have used D for the distance. Anyhow, it's distance. Some books use S, some use D. S is equal to S0 plus V0t plus 1/2 AT squared. Okay? You know the distance of travel, which is h. S0 is 0. V0 is 0. You're given the time that it takes to travel that distance, so it's very easy to calculate A. Now, with that A, the acceleration here, you can use the very definition of velocity and acceleration to figure out what the velocity is here. And that is that the velocity is equal to acceleration, its average acceleration that you just calculated, times the time. Okay, so in this case I did the math here, and velocity came out to 2h over t. Okay, now we know that for the velocity down here, and we can plug it in right there, and we can plug it in for this V up here, which is the omega, V squared over R. All right, once that plugs in, the R's cancel out, okay? So the only thing you don't know then at this point is big M, the mass of the rotor. Okay, so that's what that's what we're able to plug in the equation. You got one unknown, and I'll let you do the math on that. So that's the problem. Sometimes, let me point this out, sometimes they'll give you the mass of the rotor and you're asked to find the tension in the wire. Okay, you can do that. You know, free body diagram of these blocks down here, mg going down, t going up, all right? You can use that, and you would be working this problem a little backwards to figure out what acceleration would be required. You would V here, come back over here and figure out the A, and once you get the acceleration and you have the total acceleration of this, you got mg, so force is equal to T minus mg, all right? And this is mass times acceleration that you would just calculate, so you can solve for T. I just want to make sure you understand the concept of translating this potential energy into kinetic energy of the block plus rotational kinetic energy of the disk, and using the kinematic equation to get the velocity that that you have down here. That's all.